In this video, we are going to study Rust, which we are going to use as the safe foundation for concurrent programming. So it provides a way to abstract all the unsafety within a safe API, and we are going to use how to do that. So first things first, what is Rust? Rust is a safe systems programming language in a sense that it provides a programmer to achieve safety, absolute safety, without worrying about all the implementation details. So the motivation here is that basically C++ is unsafe. That's the reason why Rust came. So the motivation is achieving safety and control at the same time. Here the safety means that if you write a program in Rust and it satisfies some condition, then it is guaranteed that when you compile the program into assembly, the assembly program should not go wrong. It is guaranteed by the compiler and the type systems. At the same time, it achieves control in the sense that it supports all the low-level features that are necessary in programming, for example, operating systems. So in our laboratory, we are also building an operating system on top of this Rust. So it supports operating systems or database management systems or all the other kinds of systems programming because it supports all the features. To this end, the prior art should be C and C++, but they are very much unsafe because as we discussed in the previous video, you can easily shoot your foot by, for example, leaking a pointer inside a spin lock. So C and C++ cannot detect such an unsafe use of API. So that's the main difference, key difference between C and C++ and Rust. So as I said, the Rust is best fit for this course because its ownership and lifetime captures the essence of concurrency. Recall that concurrency is fundamentally about shared mutable states. And in order to reason about these shared mutable states, a notion of ownership and lifetime is very much useful because they are fundamentally about sharing, safely sharing resources. So Rust provides such a tool, and we are going to use it to program concurrency. So here are a few assignments. I want you to read the book, which is the book about Rust, and the book is consisting about 20 chapters, and each chapter is not so long. And after reading all the book, the final chapter is about building a parallel web server, and homework one is about extending this parallel web server and implementing thread pools and caches and control C handlers. So that is about the homework one. And in order to do homework one, you probably should read the entirety of the book. And it's not that long, so please read the book. And the second reading assignment would be reading a book that is named Rust by Example, that enumerates many examples in Rust programs. And these examples let you have a hands-on experience on the Rust compilers and Rust type system. And they are very much more practical than the book because it contains all the examples. So please read the book. And there will be also programming assignments throughout this course. I expect there will be 5 or 6 assignments in this course. And all the programming assignments will be in Rust. So you need to write down some Rust programs for assignments. So please set up your programming environment on the provided server or your own machine. So we support only Ubuntu 20.04, and any machine with the Ubuntu that version is okay, but probably you want to use machines with many cores. So that's the reason why we provide servers. Anyway, set a programming environment and make sure that you can compile, for example, a Crossbeam, or for example, you can compile the homework. So if you can compile and run the web server, that will be probably okay. Okay, now let's start looking at examples. Here is an example that shows the power of the Rust. So here is a function that is named main, and in the main function it is first declaring a vector of size 3 that is consisting of 1, 2, and 3. So v is a vector of size 3. Now p is the pointer to the first element inside this vector. So p gets the pointer. And now you're going to push 4 to the end of the vector. So now vector becomes 1, 2, 3, and 4. And after that, you are going to print the value inside p, v1 colon the value, which is inside this pointer. Okay, so far so good. But as many of you already know, it is very much unsafe. The reason is that the push operation may relocate the underlying vector. So vector is allocated inside a heap, right? And inside the heap memory, 1 through 3 are stored. But if you push 4, it may be the case that the size is the heap memory can no longer contain all the values because the heap memory is size 3. So you need to relocate. In other words, you need to allocate new heap memory that has a size at least bigger than 3. So, and copy all the values from the old heap to the new heap. And if it happens, the pointer here, pointer to the first element of v, may be invalidated because the underlying vector buffer is relocated. So that's the reason why it can be unsafe. It can be the reference to an unused memory area, which may invoke a page fault handler. So you can just click this link to go to the example that you can play with on your browser. So if you click on this link, there is a IDE that is running inside your browser, and it will compile this file, and then you can execute it, and you can see the compile error messages as well. Okay, so in C++, this code can be compiled. Yeah, it is bad code, but anyway, C++ allows you to do that because it cannot detect the errors or bugs in this program. On the other hand, it is not compiled in Rust because of this message. So it says this and then reject this program. Cannot borrow v as immutable. Here at this line, v.push cannot borrow v as immutable because it is already borrowed as immutable. So it is saying that v is immutably borrowed here at this line when you are getting a pointer, and then because of that you cannot borrow v in this line mutably because it is already immutably borrowed. So it is the reason why Rust rejects this example. So let me explain this bit a little bit more. V here is the owner of the vector. Vector is inside the heap and is owned by this v. V is the name and it is the owner of the vector. And here p is immutably borrowing the vector because you're going to reference to the first element of v here, and this p is later read here in order to print it. And from this line to this line, the vector v is borrowed by p. P immutably borrows the vector from the second to the fourth line. And at the same time, v.push v here at this line, this line is mutably borrowing the vector as well, because you're going to push the value. So you need to borrow it. But at this time, you need to mutably borrow it because you are going to mutate it by pushing the value 4. Now, it is the compiler says that, oh, there is a conflict between the two operations or two agents because the type checker detects that there are shared mutable accesses, P and v.push. They are shared mutable accesses. So P is also accessing the vector, borrowing the vector, and this v.push is also borrowing the vector. And one of them is mutable. So that's precisely the reason why it might go wrong. You cannot guarantee that P is good. P is a good reference because V can be changed in between. So as a result, at this time, P cannot be read safely because it may be the case that V may be vastly changed in between these two. Okay, so far so good. Then how to detect such a conflict, such a shared immutable accesses? So how to systematically detect those kind of conflicts in Rust? It is by calculating what is called a lifetime. So here there are owners or borrowers of the vector VP and the line that is executing v.push. V's lifetime is from line 1 to 5, 1, 2, 3, 4, 5, and P's lifetime is 3, 4, and 5, and v.push's lifetime is just line 4. The lifetime is basically the range in which the agent is living. V lives from here to here, and P lives from here to here, and v.push lives just at this line. So that's basically a lifetime. And you can list up the pairs of overlapping lifetimes. For example, V and P are overlapping because they are executing at the same time at line 3, 4, and 5. V and V push dot are also overlapping, and P and V push are also overlapping as well. So all pairs of these three are overlapping, at least at line 4. And now you can safely ignore those that are borrowed and borrowing. So single object. For example, V is borrower here, and V is a borrowee, and P is a borrower. The vector is borrowed from V to P at this line. So there's a relationship between V and P. They are borrowee, and borrower. Similarly, V and this v.push are also the same. V is borrowed from here to here. So you can safely say that, oh, they are safe. Even though they are overlapping, one is borrowed and one is borrowing, they are happily coexisting. But P and v.push are different. They are not a borrowed and borrowing relation. P and v.push are coexisting, but they are not happily coexisting. So that's the reason why the remaining pairs, for example, V and v.push, are regarded as a conflict. They are shared immutable accesses that can be potentially dangerous. And because they are such a pair, Rust just bail out and refuse to compile by saying that, oh, cannot borrow V as mutable because it is already borrowed as mutable. It is precisely the reason why P and v.push can conflict. You cannot do v.push because it is already there a P. So this kind of reasoning is statically sound. At compile time, you can detect all conflicting shared mutable accesses at compile time. So without any missing, you can statically figure out the entire pair of conflicts. But on the other end, it may be incomplete in the sense that not all pairs are actually conflicts. I mean, even though the program is safe, the Rust may reject this program based on the fact that it cannot analyze the ownership relationships between the agents. So it may happen, but in practice, it is not that difficult to cope with the compiler. You can just move the code around a little bit and make it happy about this ownership. So the moral of the story is that, yes, it is statically sound. It is very much important. Unlike C and C++, Rust can detect all the bugs relating to ownerships and lifetimes and memory safety at compile time. That's the main difference from C and C++. And how it does that? It is based on the lifetime and borrowing concepts that is explained with this example. Okay, let me summarize what's going on behind the scene for this example inside Rust. So the key concept of Rust is ownership. The ownership is the ability of an agent to access and destroy a resource. And if you have an ownership of a resource, for example, a vector, then you can safely deallocate it, or you can safely push a value to that, or you can safely pop a value to that from that. Okay, and ownership is by default exclusive. It means that if I own a resource, if I own a vector, then no one else can own it. The vector is only owned by me. But in order to allow sharing, it can be borrowed. So even though the ownership to a vector is exclusive, it can be borrowed by, for example, P. So it can be mutably borrowed by a single agent or immutably borrowed by multiple. So in this example, v.push is mutably borrowing the vector. But the fact is that if it is mutably borrowing a vector, no one else can borrow the same vector at the same time, because I am temporarily writing the value to this vector, so no one else can read it or write it. That's the reason why mutable borrowing can happen only for a single agent. On the other hand, the same resource can be borrowed by multiple agents if it is immutably borrowed. If multiple agents are only reading the resource, then it is very much okay, because there is no shared mutable mutations. So this is the key invariant behind this ownership. You can mutably borrow a single resource, or multiple agents can immutably borrow the single resource. This idea, again, is fit for concurrency, because each thread can be considered as an agent. So it is an agent that is accessing resources, and by the borrowing rule, you can be quite sure that a resource cannot be shared and mutated at the same time, because it is mutably borrowed by only a single agent or immutably borrowed by multiple agents. So Rust type checker is statically enforcing this discipline: no shared mutable accesses to an underlying resource by default. So the type mandates the rule here, the mutably borrowed by a single agent or mutably borrowed by multiple agents, and this is statically enforced by types. So this is the ownership principle, and it is quite easy to use in the sense that if you violate any ownership, then compilers will report every violations. So for example, in the previous example, when P and v.push are conflicting with each other, the compiler just detects the line where the ownership principle has been violated, and you can be immediately knowing that where the ownership problem happens, and you can easily pinpoint where to fix. And as I said, it is statically sound or correct in the sense that if a program is type checked by the Rust compiler, then it is guaranteed that the program doesn't go wrong in any case. So because this ownership principle is enforced to a program that is type checked, there is no way the program can go wrong. For example, if you manage to fix this example so that the program is compiled by Rust, then it is statically guaranteed that the program doesn't go wrong in any case. Okay, so far is what is explained with a previous example, but it is not the end of the story. So for concurrency, we specifically need a third story that is about bending the discipline, bending the rule with what is called interior mutability. So the motivation here is that this discipline, no shared mutable accesses, is too strong. So in concurrent programming, it is never satisfied by the actual real-world programs. For example, if you are having a shared stack, shared among multiple threads, then it is quite intuitive that this stack resource is mutated by multiple threads at the same time. There are actually shared mutable conflicting accesses. So we need to tame it, but we should not remove it because it is the essence of this shared stack. But what we can hope for in Rust is that, okay, we can systematically bend the discipline. We allow shared mutable accesses for a stack. But we can do that in a safe manner, systematically safe manner. So shared mutable accesses are inevitable in concurrency, but we can tame it. How? We can envelop possibly unsafe implementation within safe API, so that, okay, there are shared stack, concurrent stack, and that has a very unsafe implementation that cannot be analyzed by Rust compiler. Rust compiler cannot deduce that the implementation is absolutely safe. But what we can do here is that, okay, we implement the stack using a very, very arcane magic. But its API is completely safe. The user of the stack doesn't need to know about all the details of the implementation in order to write a safe program. The user knows only API, which is absolutely safe in the sense that if the stack is used with only this API, then the same guarantee is applied. The program doesn't go wrong always, as far as the API is used. In any combination of these API invocations, doesn't go wrong. That's basically the meaning of this interior mutability. So, in a sense, what is enforced by this interior mutability or systematically bending the discipline is that the concurrent stack is working as if there are no shared mutable accesses from the viewpoint of the user who uses the API. The API is as if there are no shared mutable accesses. So let me show you an example of this, of interior mutability. A ref cell is the first example of the interior mutability. And it is basically containing a value, and you can borrow it, or you can mutably borrow it. But unlike the usual references, you can mutably borrow it and borrow it at the same time. So let me explain it in a little bit more. So here is the code. You can say that there is a function f1 and f2, and there are a function returning a value, Boolean value. And let's assume that by some complex invariant, it is not happening that f1 and f2 are returning true at the same time. So it is implemented in simply by returning a simple value. But let's say that there are some complex invariant, and it is more complex, and the invariant is that f1 and f2 doesn't happen at the same time. Okay, and let's look at this program. There are two values, v1 and v2. And you're borrowing a value at here p1 depending on the condition f1. If f1 is true, you're going to borrow v1, and if f1 is false, then you're going to borrow v2. And in f2, if f2, then you're going to borrow v1 and write to the value, write to the v1 and read to the v1 as well. And after this if condition, you're going to print the value of p1. And you can see that there should be a ownership conflict, because p1 is borrowing, p1 may borrow v1 from here to here. So yeah, p1 is actually borrowing v1, but you don't. So suppose that Rust cannot analyze f1 can become true or false. It is just an opaque value. Rust doesn't know precisely the value of this f1. As a result, Rust should safely deduce that either v1 or v2 can be borrowed at this line, but it doesn't know what is borrowed. Anyway, v1 or v2 are borrowed here until the last line. So in particular, v1 may be borrowed from here to here. But at the same time, in this if condition, v1 is also borrowed mutually from here to here, right? And there's a conflict. v1 is borrowed by p1 and p2 at the same time from here to here. So that's the reason why Rust rejects this program by saying that, v1 is mutably borrowed, cannot borrow v1 as mutable here at this line, because v1 is also borrowed as immutable at here. So the Rust compiler will pinpoint where this ownership conflict happens. So you need to fix it. Okay, so far so good. Rust cannot deduce the safety of this program, but you, the programmer, know it is actually the safe. Why? Because f1 and f2 cannot happen at the same time. So if f1 is true, then v1 is borrowed here, but f2 cannot be true at the same time. So v1 is actually not borrowed at one time. Otherwise, if f2 is true, then p1 is borrowing v2, and it is borrowing v2, and this is borrowing v1. They are not sharing, not borrowing the same resource at the same time. At one time, you know that. But Rust compiler doesn't know that. That's the problem. So in order to program like this, you need a ref cell, basically. Ref cell is basically a wrapper around the value. It is a value 42. It is a value 666, but it is wrapped by a ref cell. And at this line of the code, P1 is also borrowing V1, but at this time by calling what is called try borrow. And it is checking if the ownership rule is enforced at runtime. Not at compile time, but at runtime. It is checking if, for example, V1 is borrowed by anyone. Here, let's say that F1 is true, and let's say that V1 is borrowed by, not borrowed by anyone. So P1 can successfully borrow it. Now, F2 is not executed at all, and it's okay. So the program is running safe. If F1 is false, then here V2 is borrowed, and you can enter this if condition, and this V1 is borrowed mutably, mutably. But at this point of time, v1 is no longer borrowed because v1 is try borrowed here at compile time. The Rust sees that, oh, it is try borrowed, and it doesn't need to track the ownership here. At this point of time, it says that, oh, v1 is not borrowed, and I am borrowing v1 freshly here, and it is very much safe and very much okay. So Rust allows this program to be compiled and run. So this refcell and try borrow mute is bending the ownership discipline. Ownership discipline mandates a statically safe program. Statically, no ownerships are overlapping. But here, ownerships seems like overlapping, but we can somehow analyze at runtime that they are never, v1 is never borrowed at the same time. So that's the reason why we can write this program in this way, and that's the reason why it can run without any hassle. It doesn't go wrong. But this is under condition that f1 and f2 are not true at the same time. But what if f1 and f2 are true at the same time? Then you're borrowing v1 here and mutably borrowing v1 here again, and it will exit at runtime. At runtime, it panics by saying that, oh, I cannot borrow mutably here. So you already borrowed it here, so I cannot borrow it again here. So it is represented by this error message. So you can play around with this example in this play Rust ground. So to summarize, refcell provides an interior mutability that is encapsulating shared immutable accesses, statically completing accesses in a safe type that doesn't involve the shared immutable accesses. So the reason why it has a safe API is that virtually or in API, it is as if there is no shared mutable accesses. Try borrow mute is immutably borrowing the underlying value. It is as if immutably borrowing the underlying value, even though it is actually borrowing mutably the underlying value. So this implementation should be unsafe. The Rust cannot reason about the implementation of this, but the fact that if the implementation is inspected by the programmer, you can just say that, oh, refcell try borrow mute is immutably borrowing the value. It is acting as if the underlying value is immutably borrowed. So that's the key idea here. So it is actually, in the implementation, it is actually unsafely accessing shared mutable accesses, but the API is as if it is not mutably accessing the value. So that's the key idea of this interior mutability. So in this implementation, you need to wrap the implementation around an unsafe keyword, and this unsafe keyword is a bridge between the API without shared mutable accesses and implementation with shared mutable accesses. You need to insert unsafe in order to implement interior mutability. And this unsafe keyword acts like the tag that, oh, the programmer needs to inspect all the unsafe occurrences. So it needs manual inspection. The Rust compiler doesn't guarantee any safety out of these unsafe blocks, but user needs to manually inspect that. So that acts like a tag. If you grab unsafe, then in Rust program, then it will list up all the unsafe blocks, and those blocks are only the only fragment of the program that needs inspection for safety. So that's basically the key idea behind interior mutability. The API is safe, but implementation is potentially unsafe, and that needs manual inspection. Okay, here is finally the example that is related to concurrency. So as I said, the C++ lock is unsafe because it can dereference the underlying value and its pointer can be leaked. But it should not happen because after releasing the lock, the underlying value should not be accessed at all. So in order to disallow this in Rust, it implements what is called the deref trait, and you can deref the underlying value out of lock guard. That is basically the meaning for this program. So from the lock guard here, data guard here, then you can dereference the underlying. You can get a reference to the underlying value, but it has a lifetime. It is highlighted here, but this data ref cannot overlive the guard. It should be destructed before the guard. It is guaranteed by the Rust type system. And it is highlighted here, but there is this end here, and end here means that this dereference target, which is meant to be this data ref, should not outlive the enclosing type, this lock guard. So as a result, data ref is not outliving data guard. And this line violates that, and as a result, it is not compiled. It says that there is an ownership problem, there is a borrowing lifetime problem. Live data ref should not outlive this guard, but it is outliving it. So that is what Rust compiler will say and reject this program. And as you can see, all the concurrency difficulties like this can be reasoned with Rust types. And that's the reason why we are going to use Rust as an implementation language for concurrency course. Okay, so far we studied Rust ownership type. And the motivation here for Rust is safety and control at the same time in the presence of shared mutable resources. And the key ideas of Rust is first, enforcing ownership discipline. By default, that means there should be no shared mutable accesses. But at the same time, it allows you to bend the discipline by using interimmutability. That allows you to control shared mutable accesses in a very controlled way. Systematically control your shared mutable accesses. The benefit is that you can safely analyze the safety of shared mutable accesses. So if the interimmutability are safely implemented within a type, for example lock or left cell, then the user of this library can no longer worry about the safety of these programs. They can just safely use without any worries because the API are safe. It is statically guaranteed. If the unsafe tags, unsafe implementations are actually correct, then all possible API usages are safe. That is guaranteed by Rust compilers. And the second benefit is that there are unsafe implementations, but they are explicitly tagged. You can only see those code. You can only manually inspect those code without worrying about the rest of the code. Okay, so that's the reason why we are going to use Rust for concurrency, which is about shared mutable accesses, and because they are well fit for these two reasons. In the next lecture, we are going to continue to study lock-based concurrency with Safe API. So many of you already know threads or atomic variables or locks or conditional variables, but you are going to study those concepts again, but in this time using a Safe API. So that is basically the topic of the next video.